Hey guys, welcome to the first lecture in Calculus 1. Well, let me tell you something before we get started. Um, I think I sent you two videos, right? The first video is with the big picture of calculus that I recorded last semester. And the second one was with some introductory material, basically doing a recap on some pre-calc material. Did you have a look at that as well? All right, that's good. The videos are pretty lengthy, I would say. Well, some people complained about this. You know, it's my job to provide you all the resources and material that I could provide. So I will provide you from now on, and before each lecture, I will provide you in advance the videos, the notes, the video lecture notes, the slides, you name it, basically everything. So in this semester, I decided to do a little bit different since I don't want to do the same type of videos again. This semester, I will rely more on the slides. So let's and we'll go something like this. Can you, all of you, see the screen? All right. All right. So everybody can see now, right? All right. So like I said, we're going to start today with functions and graphs. As you will see, we have the slides. I'll try to go as not as fast as I can, as slow as possible. And if you guys have any questions, please don't hesitate to interrupt me. All right, so today's lecture will be about functions and graphs. And I think, and I hope you guys looked at the video from last semester and also the notes. It's good to have an idea of what this is beforehand. So this will be very important, these notions, functions and graphs, especially when we will deal later on with the continuity and especially with differentiability. You'll see that we will need to sketch the graph of a function. Sketching the graph of a function is not as easy as you might think. It will rely on some properties that will be learned later on in the course. But in today's lecture, I would like to go over some very basic material about functions and graphs. And let me start with graphs. So what is a graph? I want you to look at this picture a bit, and now maybe I'll write over the slide. You see, the graph is a collection of all points. You see, the graph of f is a collection of all points of coordinates x, f of x, right? And you will see here in the picture, let me just say that we have something like this. So this is the graph that you see here, this squiggle here in red. And here, this dot in black, you see a point. So this is a point. Let me call this point M, right, of coordinates x, f of x. So that, right? You can, the graph of f, we say that is the collection of all such points. For example, you can have, let me draw another one here. For example, we have another one here, right? If you look at this dot in blue, everybody can see it, I hope. You will have another point, let's say x1. And here I'll have, okay, let me not just, and here I'll have f of x1, right? So here will be the point, let's say n. So here, well, let me put it like this. So n of coordinates x1, f of x1. right? And so on. You can consider some other points here as well. For example, this goes all the way here, right? So the collection of all such points will be what we call the graph of f. So this guy here will be nothing else than just the collection of these points, such points, xf of x. And we write this in a certain way, g of f sometimes. We write it as this, x, the set of points xf of x. Sorry about that. Ouch. Right? Xf of x, and x, let's say, is a real number. By the way, I have a request. If you guys log in very late, it's hard for me to I have to interrupt the lecture to, anyway, so I'll wait from now on only 10 minutes after the start. So those of you who are late 10 minutes, I don't want to interrupt the lecture all the time. I'll make myself clear. I'll write you an email about this. So this is the graph of f. And now I can show you an example. I'll write an example here before we go with other stuff. For example, if you have this function f of x to be, let's say, 2x plus 3, f defined on R and R. Well, you know how to draw the graph of this. The graph of f will be a line. But also, if you want to see what is the graph of f, so the graph of f will be, just like we said, the collection of points of coordinates x, f of x. So for example, if you plug in x equals 0, you'll get f of 0. And f of 0 will be 3. So you'll have that this point, let's say 0, 3, is on the graph of f. And to draw the graph of this function, you only need 2 points. But anyway, let's see more. For example, if you have x equals 1, you'll have f of 1 will be what? Can you tell me? So f of 1 is?
4.
F of 1 is 4. 2 plus 5. All right, so f of 1 is 5. So the point of coordinates 1, 5 is again on the graph, of f. On the graph of f. Right? All right, and now you can keep going. You can plug in x equals 2 or x equals -1. So for example, let's do one more. Let me write it here. X equals -1. You'll get f of -1 will be, what is f of -1?
1.
1. So the point -1, 1 is on the graph. Right? All right, that's what you need to know. Right? So this is a function, and the graph of this, well, I don't have enough room now, but probably after I'm done with the slides, we will draw some pictures as well. Well, the graph of this, this function here, so this guy here, is what we call a linear function. So the linear function, the graph of a linear function will be nothing else than just a line. Let me write here. So the graph of a linear function is a line. That's what you have to know. Well, if you look at this picture here, you'll see that this picture, right? This red one, this is not a linear function. You see, it goes up at some point, it goes down, and then goes up. Well, you can just by looking at the graph, you can see something. You can say that the function, the graph is rising, then it's right. But anyway, we'll get there at some point. So that's what you, at this point, what you need to know is that the graph of a function f is nothing else than just a collection of all points of coordinates x, f of x, right? All right, let's move on. Now, I would like to, how do we know that the graph of something represents a function? So how do we know that? You see, there is the so-called vertical line test. And well, a curve in the plane, right? And you'll see, I will explain immediately these two pictures here, these two pictures below. A curve in the plane is the graph of a function. This is important, if and only if, so it goes both ways, intersects vertical lines no more than once. Right? So once again, a curve in the plane is the graph of a function if and only if it intersects vertical lines no more than once. So as you can see, this is the first picture, we do have a function. And in the second picture, can somebody recognize, tell me what this is? So this is the graph of a function. Let's write it. Of a function, indeed. But what about this guy here? What can you tell me about this guy? Does anybody have an idea what this represents? What is this? What is it?
A circle.
A circle. So this is a circle. So as you know, the circle it's parameterized by as this x squared plus y squared with its center of the origin, but in our case this guy is not. So let me write it in this way. Is x minus a squared plus y minus b squared equals r squared, where r is the radius, right? So it will be centered somewhere around here, right? God knows what this point is, but anyway, so this is our, so this is a circle. So this is not the graph of a function, right? All right, so this is how you see if you're dealing with the graph of at first, if you are dealing with the graph of a function or not. All right. Now, let me tell you more about properties, about the properties of functions. And this will be important because especially when at some point when we would like to draw the graph of a function, we will need these kind of properties. So in other words, we would like to see some kind of symmetry properties. And we will say that the function, we will have two types of functions. So we'll be called even functions or odd functions. So now, in this case, a function is called even if f of negative x is the same as f of x. So it's symmetric, right? That's what for all x in the domain of f. So this will be symmetric with respect to the y-axis. And if you look at this picture here, you see, this is the y-axis here, right? This is the y-axis. This is the x-axis. As you can see, it's symmetric with respect to the y-axis, right? You see the graph? It's very symmetric. So when you have a graph that looks like this, you can definitely say that the function f is even, right? It's symmetric with respect to the y-axis. That's what you have. This is the picture that you should have in mind. And well, formally, you can write this as in the following way. F of x is the same as f of negative x. All right. Now, I have a question. Can somebody tell me an example from the top of your head of an even function?
Quadratic.
The quadratic function, the simplest quadratic function, right? So let's see. Example. F defined on R and real value. F of x equals x squared. Right? So is even because f of x is the same as f of negative x, right? Negative x squared, negative x, everything squared is, right, negative 1 squared times x squared, but negative 1 squared is 1. So there you go. Is it clear for everybody? Right? So, which is equivalent with x squared is the same as negative x squared, right? Which is true. Right? For example, if 5 squared is the same as negative 5 and everything squared, right? It's negative 5 times negative 5, which is 25. So that's what we call, this is what it means for a function to be even. And anyway, and also when you have the quadratic function, you see the graph will be a parabola, right? It will be symmetric with respect to the y-axis. Okay. All right. Now, we have seen here with the even, now let's see what happens when we have odd. Again, like I said, we can also have odd functions, not just even functions. So we say that a function f is called odd if f of negative x is, this time is not f of x, is negative f of x. Do you understand? So that's the difference. I mean, look back. You see, f of negative x, for even functions, we had that f of negative x is f of x, but now for odd functions, we have f of negative x will be negative f of x. Well, with this, for all points x in the domain of f. Well, with this taken into consideration, well, at this point, we can say that the function is symmetric with respect to the origin. So as you could, so in other words, this will be very important for you to know. F of 0 will always be 0 for all odd functions. Always, that's always going to happen. Right? Also, well, and this is, you see, is similar to the even one, similar with when the function is even, but you have just a negative extra sign here. We will see examples. Do you have an example? And also keep in mind this, that is symmetric with respect to the origin. This is important for you to know. So in the case of even functions, the graph was symmetric with respect to the y-axis, but now it's even more, it's more specific, it's symmetric with respect to the origin. All right. Can you tell me an example of an odd function?
X cubed.
X cubed, right? For example, f of x equals x cubed. Example. Right? And why is that? Well, let's see. Who is f of, so is odd? Because, let's see, f of negative x is negative x cubed, right? Which is nothing else than just negative 1 cubed times x, right? Times negative x. So this would be nothing else than just, sorry, wait, let me write directly. So this would be nothing else than just negative x squared, negative x cubed, right? Which is negative f of x. That's it. All right. Now I have another question for you. So we have seen what it means for a function to be odd, for a function to be even. And now, what do you think? Do you think all functions will be odd or even? Or there are functions that will be neither of them or both of them at the same time? Well, both of them at the same time is, well, what is the function that it is that is both at the same time odd and even?
There's none.
Circle.
I said the circle is not a function. I said which is what is the function that can be both odd and even?
There's none. Is there?
Well, what if we have f of x equals 0? What do you think about this?
Wouldn't it just be a straight line across the x-axis?
Well, f of x equals 0, yes, but it's actually the constant function 0, right? And if you look, it will satisfy f of negative 0 is the same as negative f of 0, right? But f of x is 0, so we will have 0, negative 0 is negative 0, which is true. But also, if you look back, f of negative 0 is the same as f of 0. But so, right? So you will have the function f of x equals 0. But now, is there a function that is neither of them? Neither, so it's neither
Yes.
odd or even? What do you think?
Yes.
Yes, there are, right? So there are functions, and we'll see an example. So let me write somewhere here. So there are functions that are neither odd or even. So that's what you need to know. Anyway, I will give you an example of a function that is neither even or odd. All right. Now, since we're talking about symmetry, what can you tell me about these two functions? For example, if we take these two trigonometric functions, sine of theta and cosine of theta, just look at their graphs. What can you tell me about their symmetry? Which one is even, which one is odd? By just looking at the graph, based on what we have said previously.
Cosine is odd and sine is even.
Wouldn't sine be Odd and cosine even?
Exactly. So sine will be odd. Look at the graph. What can you tell me about the graph of sine?
If you put it over the y-axis.
Symmetric with the origin.
Is symmetric with respect to the origin, right? So let's write this. So the graph is symmetric with respect to the origin. And what about the second graph? What can we say? That the graph is what? Symmetric? With respect to what?
The y-axis.
Exactly. With respect to the y-axis. Oops, sorry. To the y-axis. Well, with that in mind, what can you tell me? The first one will be what kind of function?
Odd.
Odd. And the second one will be even. Right? That's what we said. If we go back, we said symmetric with respect to the origin, so that's what we call odd. And if we go back here, it's symmetric with respect to the y-axis. Okay, right? All right, so these are two examples. So keep these in mind because we will use the symmetry of these two functions later on. And now let's look at, I want to do an example. So let's look at this example. So we would like to determine the symmetry of these functions. F of x is 3x squared plus 2, sorry. The second one was g of x is 2x cubed minus x. And the third one, h of x is x squared plus 3x. We would like to determine, when we say we would like to determine the symmetry of these functions, what do we mean? We mean that we would like to determine which function is even, which function is odd, correct? So think about it for a second. What is your hunch? What about the, let's say, the first one?
It's even because of the exponent.
Of the x squared, right? So you will be tempted to say it's even. Okay. And what about the second one?
Odd.
So the second one, you will be tempted to say that it's odd, correct? Because you have an x cubed. But you also have a negative x there. But anyway, we'll deal with that. And what about the third one?
Even.
Even, huh? All right, we'll see. It's a bit tricky here, but anyway, we'll see. So the first one is indeed even, because if you look at f of negative x, and you just plug in, instead of x, you plug in negative x, you'll have that f of negative x will be nothing else than just 3 times negative x, everything squared, right, plus 2. But like we have previously seen, we know that the function x squared in particular is even. So therefore, by just a constant, by adding or subtracting a constant will not influence, will not have an overall influence on our function f. So we will get that f of negative x will be f of x, right? I think this is pretty clear. Now, let's see the second one. The second one, as somebody predicted already, is odd, because we'll have, again, x cubed, and we have seen that x cubed is an odd function. And again, And this will have a little bit more influence over the function because we also have to subtract minus x. So this might give us some headaches, but not that much, fortunately, which is great. So g will be odd because if you evaluate g of negative x will be 2 times negative x everything cubed minus negative x. And you see, you'll get exactly negative x cubed will be 2 times negative x everything cubed will be negative 2x cubed, and negative x will be, of course, positive x. So this will give us the negative 2x cubed plus x, which is nothing else than negative g of x. So g of negative x is negative g of x. So that's what it means for a function to be odd, right? But what about the third one? What do you think about the third one? Let's see. What does your intuition tell you?
Is it odd?
Well, somebody say odd. Does anybody think it will be even or something?
Also,
Even.
I think it'll be
Yeah, I think it's even.
Even?
One. It's gonna be
Well,
neither.
guess what? Is neither. So the function h is not symmetric. So in other words, let me write here, h is neither odd or even. So that's what we mean is not symmetric. Why? Well, why do you think this is? Well, if you evaluate,
Is it because the 3 goes from negative to positive when x changes from negative to positive?
well, if you evaluate, let's evaluate h of negative x, for example. So what is h of negative x? Will be negative x squared plus 3 times negative x. So we evaluate. All right, so this would give us what? This would give us x squared minus 3x, correct? And negative h of x is what? Is negative x squared plus 3x. So there is no way these two are equal. And moreover, there is no way, right? So from here, you can say that h is not even or odd, right? Definitely h of x is not h of negative x. We can clearly see that. And moreover, h of negative x is definitely not negative h of x. So as you can see, this is an example of a function which is neither odd or even. And you see, look at the difference. Just look at these three functions. You see, okay, let's forget about the first one, but look at the last two, g and h. You see, there's not a big difference between them if you look at them, right? You see, you have for the function g, you have 2x cubed minus x, and for the function h, you have x squared plus 3x. You see, you just have an x cubed, which will, and a negative x, which by somehow it will make the function odd. But when you add, and okay, look at the function h. You see, it's a combination of x squared, which we know is even, right? And 3x, right, which we know is, how is the function x, for example? 3x. Is it even? Is it odd?
Odd.
Odd, right? You see, you have the sum of an even and an odd function, and you probably will guess like, okay, maybe it should be odd or even, but it's neither of those. All right, I hope you have now an idea of how to look for the symmetry of functions. And now let me show you some graphs. You see, this is what the probably I think you have seen the. Did you see that that meme with the cow that has his? So that's exactly, and they say in those memes like the horn is like the graph of a quadratic, then a cubic, and or the identity and so on. Anyway, so this is the picture we're talking about. You see the identity y equals x. You see it goes through the origin here. So this is the origin. This is the point of coordinate 0, 0. Right? This is the graph of, this is the simplest linear function. We also call this the first bisector, but anyway. This is the graph of y equals x. So you see, as you can see, it's a straight line. Now the second the second function, if you look at the graph, again, it goes through the origin, so the point 0, 0. But this time, you see, it's the quadratic function, the simplest quadratic function, which is y equals negative x, right? Well, if you look at the graph, you can see that it's symmetric towards with respect to the y-axis, right? Also, if you look at the cubic function, will look like this. Again, this will pass through the origin. Well, we took the simplest identity, quadratic and cubic, right? So this is the graph of the cubic function, y, the simplest cubic function, y equals x cubed. And now, well, we will have a special function. If we just take the absolute value of x, right? We'll study more this function. Again, you see there are two lines that are connected at the origin. We'll see later on that we'll study this function for differentiability purposes. And now we will also have some other graphs of functions. If you look at the square root, right? You see it again. Y equals square root of x. Of course, you cannot have negative values, so it has to go through there. So the graph will be like this. Imagine the graph of square root as the graph of x squared, but turned upside down, like on the y-axis. You see, you have only this part, only the non-negative part, because you can have you cannot have a square root of -1 in the real numbers. Well, you can have them as a complex numbers, but anyway, that's a different story. And also, as you can see, in a very similar fashion, again, well, if you, okay, let me do this. You see, if I turn the graph now like this, oh, nah, anyway. It's nothing else than just the graph of y equals x cubed, but you, right? But this time we will have the cube root, y equals cube root of x. Also, the graphs of, and probably we'll sketch this at some point, we will see why the graph of these functions look like this. So we'll have the reciprocal, y equals 1 over x, and you see In this case, well, let me go back here. Here we have the origin again. But here in this case, the origin is gone, so we don't have it. Y equals 1 over x. Of course, 1 over x, well, it's as you can see, is a rational function, and you must avoid the values for which the bottom, well, the denominator is non-zero, right? So for the fraction 1 over x to exist, we must, the condition of x is different than 0 must be met. And also in the same fashion, you can have the reciprocal square. So you have the graph of y equals 1 over x squared, right? If we consider the graph of x squared, the graph of square root of x, why not consider the graph of 1 over x squared? So the reciprocal squared. And as you can see, again, we have to avoid the value 0. So you see the graph is symmetric with respect to the y-axis, right? Anyway, so these are basically the graphs of these functions. You'll get to look at them once I send you the video. And let me show you something a bit more. Why not show you some trigonometric functions? You see how weird this look like, especially the secant one. The tangent one looks very nice. You see, it's they're somewhat symmetric. And you will see why this will happen when we will study more in detail these functions. Also, the secant square, this function secant, right, will have a graph like this. As you can see here, the tangent can take this value 0, 0, so it will pass through this. But in the case of the secant, we'll avoid this value. Anyway, as you can see, if you look, there are a bunch of quadratic functions turned upside down, but they will avoid 0. So this is how the graph of secant will look like. And now, I would like to talk about classification of functions. This is very important. So we have seen how to look at the graph of functions, but now we would like to classify them. And the first class of functions are what we know, the polynomials. So the polynomials are functions that look like this. I want you to look at them. Right? They're functions that look like this. F of x is an x to the n plus an minus 1 x to the n minus 1 plus a1x plus a0. So that's what a polynomial is. So n is the degree of f, right? And we will write this as deg f equals n. An is the leading coefficient, so it's the coefficient of the dominant, let's say, monomial, what we call this, you see. Basically, this, what we call the dominant monomial, is x to the greatest power, so that's the coefficient that you see here. But also we will have that, the constant term, which is a0, but we will also have here a term. Oh my. Looks like Siri has some. Anyway, and here we'll have x to the power 0, which is 1, right? So it's the coefficient of x to the power 0, so which is 1. So that's what we call the constant term, right? So this is what a polynomial is. And for example, okay, I'm going to ask you now. Is the linear function is a polynomial function? It is, right? When we take n to be 1, for n equals 1, what do we get? We have f of x is a1 x plus a0. So that's the linear function. What about n equals 2? So for n equals 2, what do we get? We get f of x is a2x squared plus a1x plus a0. So you see, this is a quadratic function. Quadratic function or quadratic, let's say quadratic polynomial, whatever. And so on. For n equals 2, you get the cubic and so on, right? So that's the first class of functions, the polynomials. And you will see how to find, well, how to deal with different properties involving polynomials. Well, you will see later on when we'll talk about limits of polynomials or continuity and so on. All right. Now, we would like to see what happens if g is another polynomial. You see, this time g is of degree m. So let me mention here, deg g is m. What do we mean by two polynomials to be equal? So we say that g equals f if and only if their degree is the same, and moreover, their coefficients alike are the same. So that's what it means for f to be to equal g, right? So there is no way you will tell me, like, for example, right? If I take f to be 3x squared plus 5x, right? And g to be 3x squared plus 5x plus 1. Well, here will be plus 0. These are not equal. F is not g, right? So in this case, the degree is the same. Deg of f is the same as the degree of g. Yes, but the coefficients are not the same. But 3 is indeed 3, 5 is 5, but 1 is not 0. So that's the problem here, right? So that's what it means for two polynomials to be equal, right? The coefficients are the same. Their corresponding coefficients degree-wise are the same, but first their degree must be the same. As you can see in this example, the degree is the same. The coefficients are almost the same. The only thing that's different is the last coefficient. As you can see, the constant term of f is 0 and the constant term of g is 1. So unfortunately, 0 is not 1, or fortunately. So these two are not equal. All right, now let's see some other type of functions. So these functions that we talk about now are what we call rational functions. So these rational functions are functions that look like this. So the functions that are the quotient, right, the ratio of two polynomials. So rational functions is the ratio or the quotient of two polynomials. This is what you need to know. Right? And of course, the polynomial q, right, when you have the ratio, the polynomial q must be non-zero. For example, as you can see here, if we take f of x to be x to the fifth plus 5x plus 5, everything over x squared minus 1. Well, if you look at this function, for this function to exist, we need to make sure that, so in this case, so this guy, so p of x is x to the fifth plus 5x plus 5, and q of x is x squared minus 1. Well, for this function to exist, we need to make sure that q of x, I know that my q, people told me that my q looks like a g, but anyway, it's a q here, it's not a g. So this is different than 0, right? So in this case, this is equivalent with saying that x squared minus 1 is different than 0. So which is equivalent with x squared is different than 1. Or x is different than plus minus 1, as you can see. So in this circumstance, this function will exist. So make sure that, so of course, we can define this. So f will be defined on R, and I will take out these two values, plus minus 1 and real value. So this is how I will define my rational function. So pay attention. This is important. Like I said, for other purposes, this will be important when we will study the asymptotes. You will see, and you will see that something happens at this point. And you can come up with plenty of other rational functions, right? You can cook whatever you want. So, but make sure that the bottom is always different than 0. So that's the thing that you need to take care of. All right. And now last but not least, well, you see the algebraic functions are constructed from polynomials using the operations of addition, so you can add them, you can subtraction, you can subtract them, multiplication, division, or rational power. All other functions are called transcendental. For example, trigonometric, exponential, logarithmic. And the prototype for algebraic functions is, for example, this one. Let's look at this example here. It looks kind of ugly, but let's look at it. You see, I have a sort of a combination here. The first function, this guy here, this is a rational function. So this guy here, right? As you look at it, this is a rational function. You just have x to x over x minus 1. Here, you need to make sure that this guy is not, the bottom is not 0. So you will impose that x is different than 1. You'll need to take care of this. So let's just, the whole thing is f of x. So you will avoid the value for which the bottom is 0. In our case, x minus 1. So x will be different than 1. And now you will add this with another function, as you see. Well, it looks kind of ugly, but let's see what it is. Let's look at it closely. You'll see that you have inside the parentheses, and you'll raise everything to the 4th power. So you have a power function. So you have a 3x minus, right? This is a linear function here, 3x. So you have no problem with this function at all. And now you subtract this ugly thing here. You see, you subtract this guy here. And let's see what it is. Oh my. If you look at it, on the top, we have the sum of a constant, which is 7 plus 2 over x squared. We have seen this. This is a rational function again. 2 over x squared. And again, for this to exist, I want to make sure that, so this guy here, let me, so for this to exist, we have to make sure that x squared is different than 0, so therefore x is different than 0. So that's what you need to know, right? And now, on the bottom of this fraction, we have x plus x, the cube root of x plus 5. We want to make sure that this is also different than 0, right? So also, let's write here. So also make sure that this guy, x plus cube root of x plus 7, is different than 0. So is this different than 0 for all x? What do you think? Well, we have to see for which value this is 0, right? I'll leave this to you as an exercise. So you have to see what happens when this is 0. You raise everything to the cube or to the power 3, and then you do some calculations. But anyway, what we need to know at this point for sure is that f will avoid these two values, x equals 0 and x equals 1. So the domain of f will be at least the entire real line except at least these 2 points, 0 and 1. And perhaps some other points, which are the solutions of that equation. X, so let's write this. So the domain of f is R except 0, 1, and the solutions of the equation x plus cube root of x, cube root of x plus 7 equals 0. And like I said, I'll leave this to you as an exercise. This is a pre-calc problem. So in a long story short, this is more or less the story with functions and graphs. And now I would like to, in the remaining time, I would like to talk to you about some functions. And let me talk about the range. And in fact, you'll see more in the notes and in the video from last semester. You'll see more about this. But I would like to say a few things about functions. Okay. Also I would like to define something, the composition of functions. So you can do some operations. And next time we will see more in detail how this will work. So the composition of functions will be nothing else than just f circ g, right, of x, so by the definition, this will be nothing else than just f of g of x. So it will be f evaluated at another function g of x, right? So that's the definition. And now let's see an example. Let's take f of x is, let's say 3x plus 5, and g of x to be square root of x. And now we would like to find f g of x and g composed with f of x. This is how we read this. All right, so let's see by the definition. So by the definition, we have that f composed with g of x is f of g of x, and this would be, so I'm going to replace in terms of x, I will put g of x, so it will be 3. So keep in mind who f of x is, so it's 3x plus 5. So I'll have 3, and instead of x, I'll put g of x plus 5. But g of x will be nothing else than what? Than square root of x. So this will be 3 times square root of x plus 5. So that's f composed with g. Now, also g composed with f. So I'll do the same thing, of x. So this would be g of f of x, which is, I want you to look closely. So now I'll look at my function g, and then instead of x, I'll put f of x. So it will be the square root of f of x. So this will be this nothing else than just the square root of, and f of x is 3x plus 5. You see? Is it clear for everybody how to compute the composition of two functions? Well, what can you say? Are they the same? F composed with g is the same as g composed with f?
No.
Is not the same, as you can see, right? They're different. So make sure you don't say that they're the same, because it's not, right? All right, guys, I think I'm going to stop here. Let me stop the recording.